I'm going to AA2 and I'll go, I'm good. Yeah, I have a problem. I teach that. So I have a question for you with that. Have you hooked up, you know, okay. I tried to do it here, and my coding computer is not that HDMI port. So, our tech guy here recommended I put a ticket in through IT, kind of over and do a right. So, because you have to have two HDMI cables, one for each side. Yeah, I heard him say that back in the training session, and I forgot to look there. Yeah. See, I thought it was simply just plug the USB port in, USB to USB. Well, apparently it has to be 1080p high resolution. So it's not going to be as simple as we thought. And, you know, I've got 25 people in class. It's hard to get it all completed. I want to use it. Use it all. I'm going to. Even our laptops work if our laptops HDMI that connect to the cable, but then you have to have another connection to the press on character. So that's something I can ask for over here too. So I'm gonna call it today, so I'll let you know. And I'll be the gatekeeper over here at least. But you know, it seemed like it was simple. But the only problem with that is that we can only get about 6 people around the table. Even 25 people, you can see it with Zoom people around above. So we got to be able to project the same. So not as simple as we thought it would be, but it's not impossible. It's not impossible.
It's like just 30 minutes later and I'm good.
There was a real smart book here, not the press, but here. I've got a presentation to we make this here. code. Okay, I gotta go. I got another problem. Thank you. Okay, I'll let you know what I can say. Bye. That's not supposed to be green. I looked out and I saw that and I said, I was talking to somebody over in Morrison. I said, oh, it's not even green. It's baby puke green. So it's like not like I want to do the weather or something.
All in finds out eventually you have to go to like the main district office anyway. So, they not count. Some verification that gets for.
Oh, he's funny. He is in my birthday.
I mean, one case.
And I have this problem.
I did.
That's what I.
So. Sure.
Almost put the other day.
Some system that told me it was wrong, but I expressed that change. I want to be one because I know this might be I don't want to get too sick before the
What do you? So not whatever you're done.
So, in the state. Yeah.
What's the strategist?
Chemistry. You can start like.
I just
You look at it.
yeah, I just looked at it, and so
So we let you go out.
let's see here.
it'll make it even harder for them.
I think you should be good to go.
Okay, great, thank you so much. Okay. It's always interesting when stuff like that happens. So,
Projector turning yellow.
yeah, that's, it happened to Dr. Malik last week when he was doing micro on his first day of class. And it turned yellow and he just kept on going. So, okay, well, that's good, I guess. So, okay. So now we can go ahead and get started. We're going to continue talking about chemistry today. And there we check. Okay. Okay. So let's see. Let's go ahead and get into chemistry. Now, everybody that's online should be able to see the slide that has the periodic table on it. I think this is the last thing that we were talking about on Monday. Okay, this last thing we were talking about were the elements in the human body. And if you can't see it, let me know. But if you can see it, you don't have to bother. So, okay, let's go away. Okay, so these are periodic table. It again represents all the known elements. There's somewhere 111 on the table over there. There's more than that now. Most of the higher elements above are artificially created. They count as an element. An element simply is a pure substance that can't be broken down into something less than the element. You know, water is not an element. Water is made up of hydrogen and oxygen. Table salt is not an element. It's made up of sodium and chlorine. Now, sodium and chlorine are elements, just like hydrogen and oxygen are elements. So in our bodies, we are about 70% water. So we are made up of about 70, a big portion of our bodies are composed of hydrogens and oxygens. We have carbon in there. All of our large molecules are based on carbon. Yeah, let me let these people come in. Okay, there we go. And all of our large molecules are made up of chains of carbons. And many of these molecules, as they're proteins, have nitrogen in there. So the big four are carbon, hydrogen, oxygen, and nitrogen. And they represent about, what did we say the other day? 96% of the human body. And then we have trace elements that make up the remaining 4% in here. So the big four, carbon, hydrogen, nitrogen, oxygen. We also use sodium and chlorine because we use salt all the time in our bodies. We have calcium and potassium. We have phosphorus. All of these elements are in our bodies in lesser amounts. Okay, now if you are an element, you're made up of an atom. Atoms are very simple structures. They're made up of subatomic particles called protons, neutrons, and electrons. And every atom, well, nearly all atoms are going to have protons, neutrons, and electrons. Even the simplest atom, hydrogen, has a proton and an electron. Doesn't have any neutrons, but every atom will have at least a proton and an electron. And it is the arrangement of the protons and electrons in an atom that gives the element its properties. So an element is, can't be broken down into anything less than an element. You can't take oxygen and break it in half into something less than oxygen. You can't take hydrogen and break it down into less than hydrogen. So an element is a pure substance. Every atom of an element has all the properties of the element. So an atom of hydrogen has all the properties of hydrogen. It will burn. It's lighter than air. It is transparent. So all these properties that hydrogen have, their atoms have the same thing. The same applies to carbon and nitrogen and oxygen and sodium. The properties of sodium are the same whether you have a box of salt with sodium and chlorine in there, or you have a sodium atom all by itself. So it is the arrangement, though, of these subatomic particles within the atom that give it its unique properties. Like sodium is different from hydrogen because of the number of protons and neutrons and electrons found in the atom itself. Protons, neutrons, and electrons are all the same. It's how they're organized that give these individual atoms their properties. So an atom of oxygen has 8 protons. An atom of carbon has 6 protons. The protons are exactly the same, just how many you have. So an atom of oxygen has 8 protons. An atom of silver has 47 protons. It's just the number and the arrangement of the protons and the neutrons and the electrons that make them all different and give them their different properties. A much higher melting point, a lower melting point. Is it routinely found as a gas? Is it routinely found as a solid? Does it burn easily? Does it burn slowly? Does it not burn at all? Will it melt instead? So now the symbol of every element we have is a letter up there, or a set of letters. And some of this is pretty simple. C for carbon, O for oxygen, H for hydrogen, N for nitrogen, K for potassium, Na for sodium. Na uses the old Latin term natrium for sodium, so we call it Na. K, the old Latin term for potassium, was kalium, so we call it K. Now, how many of these are you going to have to know in your professional lives? Well, not many of them. we know that sodium chloride, table salt, is NaCl. It's made of sodium and chlorine. At least we didn't have any funny, term for chlorine. You're gonna, we'll see things like hydrochloric acid, an H and a Cl, or as I said, sodium chloride, or water, good old H2O, 2 hydrogens and an oxygen. We're not going to have to remember a lot of specific formulas in here. Even in healthcare, of any kind of healthcare, there aren't many that you're going to have to deal with, but there are some, that you'll use all the time. Oxygen, carbon, hydrogen, nitrogen, potassium, sodium, chlorine. Those are the ones that you're going to use more frequently than others. So I said this already, but I'll say it again. The structure of the atom is made up of 3 subatomic particles: protons, neutrons, and electrons. Protons have a positive charge. It's an arbitrary charge, but we don't measure it per se as anything special. It just has one positive charge on it. It has one, what we call an atomic mass unit. So just now that I've said that, just go ahead and forget the atomic mass unit and just remember that it has a mass of 1. So one proton has 1 positive charge, and it has a mass of 1. Neutrons also have a mass of 1, but they have no charge. Neutrons are neutral. So if you had an atom with 1 proton and 1 neutron, it would have an atomic mass of 2 if you'd add up the individual masses. And electrons have a negative charge. Electrons have no weight, but they balance out the protons. For every proton you have, you're going to have an electron. We always have for every positive charge, we're going to have a negative charge. For every negative charge, we're going to have a positive charge. So we always stay balanced. An atom will always have the same number of protons and electrons. So for example, if I were to ask you on a test, how many electrons are in carbon? And if you look over on the periodic table and you see that carbon is number 6 up there, that 6 also means something. 6 is its atomic number, and that tells you how many protons are in the atom. It also tells you how many electrons are in the atom, because the proton number and the electron number are exactly the same. If it says 6, well, that tells you the number of protons. It also tells you the number of electrons. So protons and electrons are balanced. Atoms are stable. They're balanced. They don't have any, they keep the number of protons. They keep the positive charges balanced by the negative charges. Now, what can be variable are the neutrons.
Isn't that where like isotopes come in?
Oh yeah, and we're going to get to that in a second here, but yes, exactly. Isotopes deal with neutrons. Neutrons, the only thing a neutron can do to an atom is affect its mass, how much it weighs. That's what a neutron can do. Neutrons don't have any charge at all. They just take up space in the nucleus of the atom. So now we find, throughout this term nucleus, just like in a cell, the nucleus is the center of the atom. And found in the nucleus, you're going to have all the protons are in the nucleus. If there are neutrons, you're going to have them in the nucleus too. They're held together with what we call, subatomic glue, the energy of the universe, however you want to call it, really strong super glue, if you will. The protons and neutrons are glued together, and the energy that is contained in the atom is contained in the forces holding the protons and neutrons together. That's where the energy is going to come from. So elements, hydrogen has a number 1 above it in red on the periodic table. Hydrogen has one proton. It has one electron, has no neutrons. It's balanced, one proton, one electron. Helium is most stable. It has two protons, two neutrons, and two electrons. Helium is what we call inert. It doesn't react with anything. In fact, if you look at the periodic table, you'll see on the far right-hand side there, you'll have helium as number 2. It has an atomic number of 2, telling you it has 2 protons and 2 electrons. It also has 2 neutrons. Directly underneath helium is neon with an atomic number of 10. Neon, the neon gas in neon lighting and stuff like that, is also chemically inert, doesn't react with anything. Directly below that is argon. Below that is krypton, and below that is xenon. So these, everything in that far side is what we call the noble gases. They are non-reactive elements that don't combine with anything. Helium doesn't combine with anything, neither does neon or argon or krypton or xenon, any of these. And so they are extremely stable. We use them for all sorts of things. What do we use helium for? Thank you, balloons, yeah, because helium, the mass of a helium atom is less than the mass of atmospheric oxygen. And so helium gases will float. We can put them in balloons. If you blow up a balloon with atmospheric air, it's not going to float. It's going to sink. But helium will let you, it'll float. Same thing with hydrogen. If we were foolish enough to use hydrogen gas to fill up a balloon, it too would float. It's also very flammable too, so you don't want to do that. But yeah, hydrogen is a very good, as we would say, a lighter than air gas. It's also very flammable too. So if we inflate a balloon with helium, it's going to float. There are other things we use helium for in industry, but a lot of it is used in to inflate balloons.
Or comic relief.
Yeah, if you want to talk like Donald Duck or something, So anyway, helium is inert. Now the number 3 atomic, number 3 element is lithium. Lithium has a number of 3. It has 3 protons, 3 electrons, and in this case, 4 neutrons. There is no pattern here in the sense that you have no neutrons in hydrogen and 2 in helium, and then you jump to 4 in lithium. There's no pattern to that. So there are a variety of combinations of neutrons for many of the atoms. So the terms we're going to use here: atomic number, mass number, isotopes, and atomic weight. So the atomic number is that number on top there that we see. The atomic number tells you the number of protons in the nucleus. Every periodic table will have a number across the top like that, telling you the number of protons. That also tells you the number of electrons, because protons and electrons are equal. So if it says 8 or 9 or 10, that's how many protons you have, that's how many electrons you have. The mass number is the number of protons and neutrons in the nucleus. The mass number is usually written underneath the letter or symbol. So in the case of carbon, we have 6 on top and 12 underneath. So we have, that's our mass number. It's also our weight. And if we look at the carbon, we say, okay, well, what does that mean? Well, that is the sum of the protons and neutrons. Well, how many neutrons do we have? Well, we know we have 12 protons because it says 6 on top. We know we have 6 protons, but it says 6 on top. 6 in the red there. And that's the number of protons we have. And if our weight is 12, that means we got 6 neutrons too. So these are not hard-hitting healthcare facts. I'll just tell you that. You're very rarely ever going to end up having a discussion in a clinical setting talking about, well, I think that has 7 neutrons instead of 6. What do you think? Yeah, it's not going to happen. So, but there is a reason we're doing this. So just I ask you to trust me for a little while. So, okay, the mass number, the number at the bottom is the sum of the protons and the neutrons. In this case, it's carbon 12. And usually the mass number and the weight are written as the same thing, even though the weight might be slightly off, further out in the tenths and thousandths column, tenths, hundredths, and thousandths columns in the decimal spaces. We don't care. We generally look at it as its atomic, as the mass and the weight is the same thing. So remember, this is not a chemistry class. Now, an atom is a little bit like a cell in that it has the protons and the neutrons clustered together in the middle of the atom in the structure known as the nucleus. So we have all the positive charges in the nucleus along with all of the neutral particles too. And the electrons then are going to be in orbit around the nucleus. The electrons will be in orbit. They will be held in position around the nucleus, orbiting. They're going to be attracted by the positive charge of the protons, but they're going to have their own potential energy that keeps them from being sucked in. So we have if this is an atom with, let's say, 6 protons and 6 neutrons here, there's 6 very powerful charges here that are positive. Neutrons have the charge. You have 6 protons here pulling things in. Now the electrons are going to orbit this. The electrons are very tiny. They have no mass, essentially. All they have is their negative charge. Now, mass doesn't matter. All the electron has to worry about is, are they balancing out the proton? Now, the problem is that all the protons are together in one spot. And so you have 6 very strong positive charges. In the case that this is carbon, by the way. Carbon, atomic number 6. 6 protons, 6 neutrons, 6 electrons. Those 6 electrons, with their little itty bitty, no mass, their electric charge is negative. It balances out each proton. But see here, all the protons are together. And so they're just all sucking in, trying to suck in these electrons. These electrons are spinning around here. They can't get away, but they can't get sucked in. So we have, this is how an atom exists. The electrons and the protons are constantly fighting against each other. The nucleus is always trying to draw the electrons in. The electrons are always trying to get out. So we stay balanced. And the way we describe this, there's 2 views on this. There's what's known as a planetary model and an orbital model. A planetary model is this. You draw it like you would draw a model of the solar system, with the sun and the planets and the moons around the planets and stuff like that. And that's a really simple way to understand how these electrons are moving and where the nucleus is and everything. The problem is that electrons are moving at the speed of light, 186,000 miles per second. And it's impossible to pin down in a drawing just where that electron is. We can't comprehend the speed of light. We can't comprehend the speed of a nerve. A nerve impulse travels at 300 miles an hour. And it usually only has to go the longest nerve in our body is only 3 or 4 feet. And that's the one here that runs down your leg. And that sends a signal at 300 miles an hour. To us, it's instantaneous. And the slow ones, the slow nerves travel at 100 miles an hour. And they're in our brain. They only have to go like a millionth of an inch. So again, it's instantaneous. So we can't comprehend that, let alone 186,000 miles per second. So our electrons are spinning around here as fast as they can. Planetary, this planetary model that, this is a highly detailed technical drawing of a planetary model. So thank you, you got it. So, it's just like looking at, remember when you were in school and you looked at the solar system and you were studying space and stuff like that, and they had the sun and all the other planets. So that's what this is. It just gives you a good idea of where the electrons are. The orbital model can't show that. The orbital model shows you a fuzzy mass because that's what really is happening. The electrons are moving so fast that if you were to take a picture of it, there is no camera in the world that is fast enough to capture individual electrons. The best you would get is a blur. The best you would get is that fuzzy mass that you see in the screen down there where the electrons are spinning around. Even the drawing on the left-hand side there, it looks like a cloud because the electrons are moving so rapidly. Even though for us, we want to understand, like in helium, we want to understand that there are 2 electrons in orbit around the nucleus. And for us, that's all we care about. We know there are 2 electrons. If it's helium, it's got to have 2 electrons. If it's hydrogen, it has to have 1 electron. That's what we know. And so, while it's nice to know the more precise structure, for us, it doesn't, I don't think I've ever had a discussion with any of my colleagues about the planetary structure versus the orbital structure of an atom. It doesn't really matter. What matters, though, is that energy that the electrons are using, whether it's either model, to keep from getting sucked in. And that's their potential energy. They're fighting back. They're fighting against the nucleus. Now, why is that important? Well, it's because if an electron's using up all of its energy fighting the nucleus, it has nothing left. But if it's not using all of its energy to fight against the nucleus, where the protons are, it has some potential energy. And it can be used for something else. When we eat food, food has calories. Calories are a measure of energy. And the calories in food are based on the location of the electrons in the molecules. The electrons in the molecules contain lots of potential energy. So certain foods that are high energy foods like carbohydrates, for example, have lots of electrons that have lots of potential energy. And that's what we pay attention to it for. So, okay. So these are the 2 models. If you were to see either one of them, you could say, well, that's, there's the electron, there's the nucleus. The reality is that, again, this is not going to affect anything you do in any kind of professional setting. So, and I like to use the planetary model because it's simple, it makes sense. It shows you where the electrons are. It shows you what the atom looks like. There's hydrogen on the left. 1 proton, 1 neutron. I'm sorry, 1 proton, 1 electron. There's helium next to it. 2 protons, 2 electrons, 2 neutrons. Helium is balanced. Its electrons and protons are equal. And there's no room for anything else to get in here. Actually, every atom is balanced, but hydrogen's balanced with 1 and 1, helium's balanced with 2 and 2, but there's no room for any more electrons. Hydrogen, on the other hand, only has 1 electron, it has 1 proton and 1 electron. Hydrogen is not stable. Hydrogen is reactive. Because atoms aren't happy, if they could be happy, they're not happy until they always want to have their shells where the electrons are located. They always want to have them filled up. So that first shell, that first orbit, An atom isn't happy unless it has 2 electrons in there. Helium's ecstatic. It has 2 electrons. It can't react with anything, but hydrogen is reactive. It's always looking for another electron. Lithium, look at lithium. Lithium atomic number 3, it has 3 protons, 4 neutrons, and 3 electrons. You'll notice that the 3rd electron is in a different orbit than the first 2. Electrons are organized around the nucleus in different layers, different orbits, different, we call them shells or orbitals or however you want to refer to it. The first orbital only ever holds 2. The second orbital or shell or layer holds up to 8. And atoms love to find a way to fill up those shells. You know, hydrogen isn't happy because it only has 1 electron in its orbit, in its shell. It wants to, you know, it's reactive. It reacts with everything so it can get another electron. Lithium is also reactive. It needs 7 more electrons in its shell. Lithium reacts with everything to try and get those electrons in there. Now, the term isotope, you mentioned isotopes earlier. Isotopes are a variation on an atom based on the number of neutrons. It alters their mass. Every atom of an element will have the same number of protons and electrons. It doesn't matter, like carbon, for example, carbon can have 6 protons and it will have 6 electrons. Most carbon has 6 neutrons, but some carbon can have 7 neutrons, and some carbon atoms can have 8 neutrons. Carbon-14, anybody ever hear of carbon-14? It's radioactive carbon. It's what's called an isotope. It's very unstable. And the reason it's radioactive is because it's unstable. An isotope has a mass number different than most of the other atoms of that element. So most carbon has an atomic mass of 12, 6 protons, 6 neutrons. Carbon-14 has a mass of 14, 6 protons, 8 neutrons, but it's unstable. And it will gradually release energy so that it can start kicking out those extra neutrons. It doesn't like those neutrons, and so it will release energy of a known quantity at a very specific rate. That's what radioactivity is. It's the release of energy by these, we call them isotopes. It's the release of energy from these unstable atoms. And we release it at a known rate, at a known quantity over time. And so carbon-14 will degrade over time. As it kicks out, it's enough energy, the glue, if you will, to kick out the superglue, if you will, to kick out a neutron. And it will continue to do that until it becomes carbon-12.
I will never unsee the image of radioactivity being just a guy peeling glue off his skin.
If it works, you know. So now, as an isotope decays, it gives off this energy, and that's where radioactivity comes from. A radioactive substance, a radioactive element, is an isotope of an atom. It's unstable. It will release a known amount of energy consistently over time. You know, we measure the amount of radioactivity through what we call a half-life, and the half-life is when we say half of the energy in that atom has been lost. You know, it takes, how long does it take to get down to half of the available energy? In the case of carbon, the half-life has been calculated to be 5,000 years. And that's a relatively short period of time. We use carbon-14 for what we call carbon dating, where we can estimate the age of an object. Sure. Where we can estimate the age of something based on the amount of carbon-14 that's present in there. Because everything has carbon-14 in it, in some quantity, some, lesser quantities, greater quantities, but it has to be organic material, like, cloth or wood or, bone or something like that. It doesn't work on metal, very well anyway. So we use, we know that some things are radioactive. What does this have to do with healthcare? Well, first of all, there's some isotopes right there. Hydrogen can come in 3 different forms. Hydrogen, plain ordinary hydrogen, 1 proton, 1 electron. It's reactive, looking for another hydrogen, but it's not radioactive. Now, if we have 1 neutron in the nucleus of a hydrogen atom, we have what's known as deuterium. Deuterium, if it combines with oxygen, will form what's known as heavy water. Heavy water is simply a water molecule that has more mass than H2O. H2O has a mass of, or a weight of 10, a proton from each of the hydrogens and 8 protons from the oxygen. That adds up to 10. But if you are using deuterium, you have 2 extra neutrons, 1 in each of the hydrogens. That gives you a weight of 12. So the water is heavier. That's where the term heavy water comes from. Another type of hydrogen atom is tritium. It has 2 neutrons in its nucleus. So it weighs even more. So deuterium and tritium are both unstable. They want to get rid of those neutrons. They kick them out and release energy. I just said all that. Now, what comes out of here are alpha particles and beta particles and gamma rays over time. As this energy, the glue is breaking apart. And given enough time, every radioactive substance, every radioactive isotope will eventually degrade down to its normal state, its stable form. Why do we care? Well, we care because we use radioactive isotopes all the time in a variety of healthcare situations. For example, we can treat thyroid cancer without surgery. We can use a radioactive isotope of iodine. See, the thyroid needs iodine to, there we go. The door won't stay shut. I don't know why. So our thyroid needs iodine to make thyroid hormone. Thyroid hormone, it controls our metabolic rate in our bodies. Got to have thyroid hormone. Without iodine, we don't have any thyroid hormone. We get our iodine usually from salt. Table salt has been iodized for about 100 years, so we don't have an issue. But if we have a patient with thyroid cancer, and you don't want to go in surgically, you can administer radioactive iodine to that patient. Now, the only place in our bodies where iodine will go and become sequestered is right here in the thyroid. It will circulate throughout our bodies, but the only place it will end up is here. And so a dose of radioactive iodine will ultimately end up in the thyroid. And you can see that's what the thyroid gland looks like. It looks like a little letter H or a butterfly. And you can see where it's glowing. You're in a glow in the dark, if you will, as the iodine ends up in the thyroid. Now, in this case, what they're doing there is measuring what part of the thyroid is working and what isn't. The dark area where it says a benign nodule is showing that the iodine went there, but nothing happened. So it means that area is not working. But where everything else is glowing, then the iodine is being taken up and helped to be converted into thyroid hormone.
And it glows because it's radioactive, correct?
Right, it's glowing here on this screen. Now, you would not physically glow,
Right.
but you would set off any radiation detector anywhere. You know, if you had a test like that, and then you went over to like you were at UT and decided to go over to the federal building downtown, you'd probably set off their radiation detectors. So, because they're, you know, I mean, you would have, we say that you glow, you know, well, you don't really glow, you know, but your thyroid does on a scan like that. Now, if you had cancer, a thyroid cancer that you needed to treat, you would still be given the radioactive iodine, but at a stronger dose, stronger, you know, a more powerful radioactive isotope, so it would kill the cancer cells. So the downside of that is it also kills all the healthy cells too, but it gets rid of the cancer, and your patient goes on thyroid hormone replacement. But so there's a variety of uses for this. There are radioactive tracers used to test your gallbladder activity that you can be scanned for. You know, it's a device that looks very much like a CT scanner, and it monitors the effectiveness of the thyroid or the gallbladder in dealing with fat showing up in the small intestine, whether or not it's going to release that. So there's a lot of things we can use these isotopes for. Yes.
Before I had my gallbladder taken out, they gave me an IV and they said that it was basically a liquid cheeseburger.
Yeah, because of the fat content,
Yeah,
because the fat was to trigger the gallbladder, so it would respond.
and it didn't work like at all, so they just took it out because it was causing me pain.
Yeah, you know, the gallbladder is one of those things that we can, they're nice to have, but we can do without them too. You know, have you had any problems since then?
Oh, yeah. It
Oh.
doesn't change.
Oh, well, okay, let me rephrase that then. In most people,
They
so-
say it takes up to 5 to 10 years for you to actually feel relief,
mhm.
but it is slowly getting better.
Okay. Well, I know my wife had hers out about 6 years ago, and she feels great. You know, she felt great right afterwards. So I guess it also depends on what underlying conditions are. See, something else, you know, our gallbladder sits right here. Our gallbladder releases a substance known as bile, and bile dissolves fat, breaks it down so it chops it up in little tiny pieces so we can absorb it and get it into our blood supply. The gallbladder is only a storage facility. The liver makes the substance known as bile. Bile is what breaks up the fat. The gallbladder stores it and releases it when we need it. Does not make it. And a common misconception is that if you have your gallbladder taken out, you can never, ever, ever enjoy anything with fat in it. And that's not true. You may not be able to eat a whole cheese pizza with a cheesecake dessert, but you know, at one time, but you can still, you know, we still have to have fat in our diet. So
You can eat it, just less of it.
less of it, yeah. So how are you about eating fats?
It's not really that. It's like corn,
Corn.
salad, anything spicy.
That's interesting. So,
Like if I eat popcorn, or if I just eat corn, or if I eat salad, I'll really tell if I eat something spicy, or if I eat like pizza, I can't eat it. It's too greasy.
okay. Yeah.
Burgers too, it's too greasy.
Yeah. I know that my wife is very sensitive to high levels of grease. So we grill a lot of foods. We smoke a lot of the foods so that, you know, we don't get a lot of, you know, left fat or anything like that. You know, and so, I mean, I don't notice it, you know, she's had this for like, her gallbladder's been gone for like 6 years. I don't really notice the difference in the foods other than the fact that we're not eating as much fat as we did before. So, I will say for most people, unless there's some sort of underlying thing like you've got going on, the gallbladder's gone and most of their problem goes away. So, salads and you know.
Greens also, is that like a different, like, is that weird? I can any kind of lettuce, spinach, greens. That was my dad's difficulty when he had his.
Really?
He
So-
loves spinach, loves salads.
Mhm.
It, like, no, it was not. They told him when he had this thing that they were like, limit as much spinach and lettuce and as as you you want. Nuts will make it hard to.
I can understand the nuts because of the small particles, and they can cause problems further on, particularly in the large intestine.
For me, like mine was never taken out, but I was given like medication
Mhm.
before I eat something like, and for me, it's like grease, but also like red sauces. Is
Mhm.
that, like,
Yes.
Yeah, yeah.
Dark
So-
sauces.
yeah.
Okay, now that I'm gonna have to look up because that's something new. I hope I never have that issue because I love spinach, you know, not out of a can, but, spinach salads and, of course, I guess the death bomb would be spinach Maria with all the cheese and the spinach together, the illusion of healthy. Oh, I'm having spinach. Well, it's also soaked in Parmesan cheese too. So, okay, well, I want to look that one up and I'll get back to you on that one. So anyway, so these isotopes though are really helpful for us, for testing and for treating. Now, I will say that a lot of, with the thyroid, we do have things like proton beam therapy to isolate the tumor and destroy the tumor without destroying the whole thyroid gland. Because, you take out the whole thyroid, you do get some complications then, as you got to replace a couple other hormones, or you got to regulate that. But there are going to be times where where one approach is better than another approach, so it's nice to have those isotopes available. There is a lot of therapy and different types of treatment, a lot of radiation treatment that you deal with cancer. And you have chemotherapy and radiation. A lot of radiation may be the administration of an isotope and not just a beam. So this actually is relevant to something you'll probably encounter in some type of healthcare. Okay. Now, elements don't usually exist by themselves. They tend to combine with other atoms. Atoms tend to combine. Atoms become more stable when they combine. Hydrogen and oxygen combine to form water because hydrogen and oxygen are more stable together than they are individually. It has to do with the presence of the electrons in orbit around the nucleus. And if you can fill up those orbits, those shells around the nucleus with electrons, then both atoms are going to be happy. Or maybe three atoms together are going to be really happy because they're more stable when they're combined. So we can, it turns out we can share electrons, or we can steal electrons, or we can just borrow electrons. Now, the term molecule, who hasn't heard the term molecule? We talk about water molecules all the time, right? Water molecule, H2O, two hydrogens and an oxygen. When a molecule is any two or more atoms that are bound together, water, hydrogen, and oxygen. The air we breathe, atmospheric oxygen, we call it O2 because it's two oxygen atoms linked together. We don't breathe elemental oxygen, just plain ordinary O, with the atomic number of 8. We breathe O2, two oxygen atoms linked together. Elemental oxygen won't work for us. So we breathe the molecular version of it. That's what we refer to. We say O2. We're talking about the stuff that you see in the hospital in a green tank, and it's what's in the air. 20% of what's in the air now is the atmospheric oxygen. So that's two atoms. Sometimes the molecules can be bigger. Glucose, for example, simple sugar has 6 carbons and 12 hydrogens and 6 oxygens. It's a fairly big molecule. Table sugar, sucrose, is even bigger. It has 12 carbons in it. So it's a larger molecule. So we can build fairly large molecules of just about anything. Now, a compound is when we have different atoms mixed together. Now, we use the term compound and molecule interchangeably. We say a molecule of oxygen, atmospheric oxygen, we say a molecule of water. We don't tend to say a compound of water, we tend to refer to it as a molecule, even though the term compound means, something that has different atoms together. We always say a molecule of glucose, or sucrose or something like that. But,
It's kind of like the state of singular versus the state of what it is.
exactly. We can say glucose is a compound, but we refer to it as a molecule of glucose. Sort of technically incorrect, but we don't care because everybody knows when you say a molecule, you're talking about, elements linked together as atoms. Now, when we look at molecules and compounds and things like that, we have to consider something else. We have to consider a mixture. Mixtures are different than molecules. In molecules, the electrons are actually being physically shared. Water, this is distilled water right here. You can't see the hydrogen atoms or the oxygen atoms in here. They're all mixed together. The hydrogens and oxygens are fastened to each other, and then the water molecules then are also fastened to one molecule is attached to another molecule to another molecule. So this is different than a mixture. A mixture is only physical. A mixture is mixing different substances together, but you can separate them out. I can't take water and just pour it through a filter and say, oh, here go the hydrogens, there go the oxygens. Can't do that. This is a 10% salt solution right here. Now, you can even see the salt sitting up in the bottom of the beaker. So it's 10% sodium chloride and 90% water. That's a mixture. We've physically mixed the salt and the water in here. I can filter it out. I can run it through a filter and get all the water out and leave all the salt behind. I can let it evaporate and I'll have nothing left but the salt. So, because there was no chemical change to the salt and to the water. In a mixture, there is no chemical change. Salt's still salt. It might be in the water, but it's still salt. The water hasn't changed. It might have salt in there with it, but it is still water. If I had one of those aqua filters, little straws, and sucked on that, I would taste nothing but water because it would leave the salt behind. So this is a mixture. Most things that we encounter are mixtures. If you're whatever you're drinking, in all your, when you've got water, so you don't count. So whatever we got, whether it's coffee or what is that? Mountain Dew? Monster. Okay. Whatever's in there, can always be separate. The sugars that are in there, the caffeine that's in there can all be individually filtered out. The same with any other thing, whatever your drink is, we could filter out the ingredients because there hasn't been a chemical change to anything here. Mixtures don't have chemical changes. If you mix up sweet tea, you could filter out the sugar because the sugar, nothing happened to the sugar inside the sweet tea. The sugar is still there. It's in solution in there, and it can be filtered out. Or you can let the tea evaporate because the tea is water, and the product coming off the tea leaves, and you could let all that evaporate, and the sugar will be left behind. Sugar is not going to disappear. the salt is not going to disappear. So now what do we use mixtures for in healthcare? Well, mixtures come in 3 different forms: solutions, colloids, and suspensions. And we've all seen these without thinking about it. A solution, it involves a solvent and a solute. A solvent is what we use to dissolve some sort of material. A solvent is usually the liquid portion of something. It is what we call the dissolving medium. So the solvent is the dissolving medium. I'm trying to learn to speak today. And the solute is the substance being dissolved. Water is the universal solvent. So in our bodies, water matters. Water is the solvent, and the solutes are going to be the various salts: sodium chloride, potassium chloride, hydrochloric acid, magnesium chloride. It's sort of a theme running here with chlorides. So all of these substances, the salts in our bodies, are going to be the solute. In this case, this is sodium chloride is the solute, and it's dissolved in the water. This water is the solution. So in our bodies, we pay attention to things like blood sugar levels. How much glucose, how much sugar is in solution in our blood? Sugar is dissolved in our plasma. That is plasma. The salt water in our bodies is the solvent, and the sugar is the solute. The solute is what's getting dissolved. So that's a solution. Solutions are transparent. If I were to stir up the salt, it would all disappear. It's still in solution, but it is a transparent solution. Nothing special. You can't see anything. Consider tea. No matter how strong you make your tea, you can still see through it. No matter how strong you make your coffee, coffee is still a solution because it is ultimately transparent. You can still see through it. I mean, it looks pretty dark and thick and whatever, but it is still a solution. Nothing has happened to the coffee when it is mixed with the hot water. There's no chemical change to the coffee or to the tea when it's mixed with the hot water. So there's a solution. Solutions are transparent. Air is a solution. We can't see the oxygens and the nitrogens in here. We can't see the trace gases, the methane and the carbon dioxide and the hydrogens and the heliums and things like that in here, but they're here. It's transparent. If we add salt to water, it's going to dissolve. If we add sugar to water, it'll go into solution. And yet the properties of the sugar haven't changed. The properties of the salt haven't changed. Our bodies are 0.9% sodium chloride in the water in our bodies, in the plasma, 0.9% sodium chloride. That's a constant. We work very hard to maintain 0.9% sodium chloride in our plasma, in the water that surrounds our cells, the water inside the cells, the water in all of our body cavities, inside our eyeball, inside our spinal column, everywhere is going to be 0.9% sodium chloride. That's what normal plasma looks like. It's 0.9%. And I think I got a bag over here. This is distilled water, and in this case, lactated ringer solution. It is sodium chloride, sodium lactate, potassium chloride, calcium chloride, and a whole lot of water in here, and yet it's transparent. Normal saline that you would use in an IV is just 0.9% sodium chloride. So they all look the same. They're all transparent. These are all solutions in here. we can't see it, but the substances are there. If we could, and if I had a filter, I could filter that out. It's very easy to filter, given a filter with a small enough hole in it, you can filter out anything. So. Yeah. Solutions, how do we measure them? Well, we measure them 3 ways. The simplest approach is percent. Simplest approach is simply percent. How many parts of the solute are in 100 parts of the solution? This is a 10% salt solution. To make a 10% salt solution, you take 100 grams of salt in a liter of water. 100 grams of salt in 1,000 milliliters of water gives you a 10% salt solution. That is the simplest. These IV bags are all going to be in percents. Doesn't say on here. You wouldn't probably want to use this because it's about 15 years old, but that's beside the point. But it says 0.9% sodium chloride. Normal saline would be 0.9%. Okay, that's fine. That means that you have for every liter of water, you're getting let's see, not 90 grams of salt or 9 grams. I can't do the math. One or the other, 90 or 9 grams. Probably pretty important to know the difference, but I think it's 9 grams of salt in a liter of water to give you 0.9% to give you normal saline. Fortunately, none of us have to make those up. They always come to you. In a hospital setting, you would have that. The pharmacy would make that up, or they would buy it commercially already pre-made. The point is, though, that percentages are the easiest way to calculate a solution. Any kind of IV is going to be in percents. A lot of medications may be administered in percents. Now that is almost everything can be measured in percentages. Now there are a few substances that are measured differently. We measure milligrams per deciliter. A deciliter is 1/100th of a liter. So we're getting down to a pretty precise number in here. Milligrams per deciliter, we use this to measure blood sugar levels. Blood sugar levels tend to be right around, a normal healthy blood sugar level should be between 80 and 100 milligrams per deciliter. So we pay attention. What's our blood sugar? Well, it's about 80, 85. The blood work comes back and says blood sugar level is 90, or the blood sugar is 300 or 600. And you've got some issues there, possibly. So we use milligrams per deciliter for things like blood sugar. We use milligrams per deciliter perhaps for looking at the number of red cells or white cells present in a deciliter of blood. So when we want to have a little more precise reading in here, that has become the standard. And the third type of solution is known as molarity. And this you're only going to get into if you are dealing with chemistry, as far as in a laboratory setting. Molarity is based on the number of moles of a solute per liter. What's a mole? Well, if you add up all of the atomic weights in a molecule, if you have, for example, glucose C6H12O6, if you add up all the atomic weight of like the 6 carbons, each carbon has an atomic weight of 12. 6 times 12 is 72. You add those up, plus the 12 hydrogens, plus the 6 oxygens, it comes out to 180 atomic mass units. If you convert the atomic mass unit to grams, a mole of glucose is 180 grams of glucose. So if you wanted to make a 1 molar solution of of glucose. I don't know why you'd want to, but if you did, you would put 180 grams of glucose into a liter of water. So you would have a molar solution of glucose. Or if you were going to have a 1 molar solution of hydrochloric acid, you would put in the molecular weight of the hydrogens and the chlorines into water, and you would have a 1 molar solution. And the more moles of a substance you have in the solution, the stronger it is. For example, hydrochloric acid, the acids are usually, like strong acids are 6 molar or 12 molar. Weak acids are usually in a 1 molar or 1/10 of a molar or 100th of a molar or something like that. So now why we pay attention to it is that for some strange reason, a mole of any substance always contains the same number of molecules. The number is called Avogadro's number, and it's 6.02 times 10 to the 23rd molecules. Why do we care about that? Well, that's sort of really the driver for the movement of water across the membrane. The term osmosis, passive transfer of water across the cell membrane, is driven by pressure based on solute particles. The more solute particles you have, the more pressure to move water one way or another across the membrane. So Avogadro's number. Yeah. The really bizarre thing is this was calculated hundreds of years ago. This guy probably would have been very good at Tetris and putting things together in his mind too. But it's just bizarre to think that this was all done long before computers or calculators or even slide rules or anything like that. So
You say they all have the same weight.
they all have the same number of particles. So okay, so that is a solution, and basically we're gonna in any kind of healthcare, 99% of what you do will be dealing in percentages of solution. The other 1% will be in grams or milligrams per deciliter, like blood sugar levels or cell types in solution. I don't think you would ever get involved with molarity or Avogadro's number or anything like that. So now the second type of a mixture is known as a colloid. In a colloid, colloids aren't transparent. Colloids are cloudy. The particles in here will not settle out. Solutions don't settle out either, so they stay transparent. Colloids don't settle out. They're cloudy. They are opaque. You have globules floating through the mixture that don't settle. They float. They move around. You have usually it's all based on nearly always based on water, but you have butterfat. In case of milk, you have butterfat floating around in the milk, and it won't settle down. So we also call it an emulsion. So it's, as we say, heterogeneous. It has different particles floating in solution. Jello is often considered an example of a colloid. Milk is a better example of a colloid. So solutions are transparent. Colloids are cloudy because the particles are suspended and don't settle out. And the third type is the suspension. The solute particles in a suspension will settle out over time. If you have a sample of blood and you draw out a sample and you set the test tube aside and let it wait, the red cells are going to sink to the bottom of the test tube and the plasma will remain above that. And so you'll see how the red cells have dropped down and the plasma stays clear. Just like, or Italian dressing. you shake it up in the bottle and let it wait. And then all the seasonings inside the Italian dressing are going to sink to the bottom of the bottle. And the oil will be in the top, and the vinegar and the water and everything else will be at the bottom, and all the particles will be at the very bottom. You'll shake it up. You know, lots of medications are suspensions. You know, you have to shake it before you administer it, you know, because it has some of the stuff has settled to the bottom. Even spray paint. You know, you're going to go to use Rust-Oleum or something, and you have to shake it up to get the paint and the solvent and the propellant all mixed together properly. Otherwise, you're going to be pressing the button and nothing's going to be coming out. And then you got a can of paint you can't get. So suspensions will settle out no matter how often you shake them up. So our blood is a great example of a suspension. Now, normally what happens with the suspension is, with blood, is we put it in a little centrifuge and we spin it around and we throw all the red cells and white cells and platelets to the bottom of the tube, and the plasma is on the top. That's what you see right here in this picture at the top on the right. You can see whole blood on the left, and you can see the different layers on the right. You can see the yellow pale plasma. If you look very carefully, there's a very thin white layer right there at the top. Those are the white cells, and then everything else are the red cells, the platelets, sensory only cell fragments are packed in through the rest of that. And so that's what whole blood looks like when it's spun down. It is, you know, we don't see it that way when we bleed. We have a sample of blood, we see the whole blood coming out. If we could separate it out, we would, it would look just like it does on the right-hand side. Suspensions. If we mix water and sand, if you're setting up an aquarium and you dump in the sand and for the bottom, and then you fill it up with water, and you get all that cloudiness, you know, it all mixes together, and then you come back in about a half an hour and the water's clear and all the sand's on the bottom. That's a suspension. You know, there was no chemical change to the sand. There was no chemical change to the water. Mixtures don't, any kind of mixture, you know, any physical intermixing doesn't cause a chemical change. You mix up concrete. There's no chemical change to the rocks and the gravel and the sand and whatever else that goes into concrete. It doesn't change chemically. You could, in theory, break that concrete apart and break it down to its individual components again, because it's all just mixed together. It's not, in the case of concrete, it's not moving because it's been stabilized, but you could grind it back up and get the separate ingredients out of it.
Pretty impressive for just being a mixture, actually.
Oh yeah, I mean, when you think about how what it can do for us.
Just out of curiosity, is the whole like blood and plasma separating, is that the same kind of thing as like what happens when you pour water and oil together and try and mix them?
Well, it sort of only in reverse, because when plasma, with blood, the heavy components sink to the bottom. You know, they will mix together. The oil and water, the oil is much lighter. You can shake it all up, but they won't mix, you know. And the red cells and white cells, they're not mixing either, but they're heavy enough that they'll sink to the bottom. The oil is light enough, it'll go to the top. It's sort of the opposite effect, but it's the same principle. You know, you end up with water somewhere, you know, no chemical changes took place. So, but no, that's not to say this is a bad thing. We use this all the time. Medicines and pharmaceuticals and drugs that we use are all going to be mixtures of substances. We're always going to be mixing, you know, various ingredients together. Many times we have to shake it up. Sometimes it's a solution, you know, like a solution of just like normal saline, for example, or normal saline with something else added to it. There's another bag over here. Here we have dopamine in a 5% dextrose solution. So it's 5% sugar water, and it contains 1,600 micrograms per liter of dopamine in here, 400 milligrams altogether. So we have, but it's transparent. Now that's the solution. There's no chemical change to any of the ingredients. It has, I guess it has to be protected from light or something. But again, you can't look at it and say, oh, there goes the dopamine right there, So so we use these mixtures all the time. We eat different foods that may have mixtures in there too. I mean, who doesn't? We drink coffee, we drink soft drinks, we drink tea, all these things. No chemical changes took place to the sugar in the tea, for example. It's still there. Now, mixtures and compounds. Compounds, let me back up here. Mixtures don't involve any kind of chemical bonding or chemical changes. The ingredients in a mixture still retain all their properties, whether it's coffee or whether it is and sugar or tea and sugar or salt and water or anything like that. There is no chemical change to those parts, those components. And you can separate them out. Given a filter small enough, you can separate out anything. There are no chemical bonds that were made here. And our mixtures can either be transparent or they can be cloudy. They are either going to be homogeneous where it all looks like this, or we can be heterogeneous like milk, for example. But compounds are different. Compounds are held together through chemical bonds. These are chemical bonds taking place here. There are chemical changes to the molecules. There are chemical changes to the molecules when a molecule is formed like this. Sure. When you combine hydrogen and oxygen in a water molecule, the properties of the oxygen and the properties of the hydrogen are now different because they're combined. It isn't, a water molecule is generally not going to float away like it would with a hydrogen atom. So we see distinct changes here because we are now physically, we are now chemically sharing electrons, and it's all about the electrons. We're going to share these electrons. We're going to share the energy stored in those electrons. So we don't have a physical change, but we have a chemical change. And it's all about the electrons because the ability of hydrogen and oxygen to come together to form water are based on the need to share electrons so that everybody is happy. Every atom wants to have all of its spaces for electrons to be filled up. Every atom wants to have as many spaces for electrons as it can have. So let me give you an example here. Here is, I'll keep it simple. Here's an atom, and let's just say it has, well, we'll keep it very simple. There's hydrogen. It has one proton. It has one electron here. It's not happy. It's not stable. It would love to have a second electron here. It's very unhappy. Atoms want to have their outermost shell always filled up. See, atoms can have, there's a nucleus, it can have one shell, it can have two shells, it can have three shells, and so on. And so the first shell will can only ever hold 2 electrons. The second shell can hold 8. I'm not going to draw 8 electrons. So if you have something with like hydrogen with 1 electron, All it needs is one more and it's happy. What if you have carbon? Carbon has 6 electrons. It has 6 protons. It has 2 electrons in its first shell, and it has 4 in its second shell. Second shell of a happy atom, of a full atom, is 8. First shell, 2, second shell equals 8. But we're missing 4 electrons. Now, why am I talking about happy shells and stuff like that? Atoms are stable when their outermost shell is filled up. And if they share electrons, they're going to be very happy. Hydrogen is very reactive because it wants to get that extra electron in here. It will combine with another atom. And the number one atom hydrogen combines with is carbon. Carbon also wants to fill up its outer shell. And so carbon and hydrogen come together very, very easily because of that. So, okay, I'm going to stop because I've probably given you more than you anticipated today. So, but we'll go ahead and pick up with this on next Monday. No, wait, no, Monday is Labor Day. No class on Monday. We have no class on Monday. Do not come. I will not be here. The building will be locked. Well, you can bang in the door, but no one's going to answer. So lab this afternoon. If you're in the lab today, we're going to take a look at the other tissues. We're going to do a little experiment with movement across the cell membrane. If we have time, we will do the cheek cells. If we don't, we'll push that to next week. So I'll talk faster today than I did yesterday. Okay, thank you, and I'll see you. I guess I'll see some of you in lab.